Alright, so now let's continue geothermal energy. Let's see what happens if you have the water coming out from the side is the water coming from the ground is not steam or vapor dominated but more liquid dominated. So you are getting saturated liquid rather than saturated steam. What do you do with that? Well, liquid water is not good for turning our turbine, right? We need steam to run this turbine. So what do? We flash it. This is the same cycle that we have seen in the open OTEC, the ocean thermal energy conversion. That what they do if they get saturated liquid from the ground. So this it goes through it, so it come here at 1, it go into a flash separator, which is basically just like a reduced pressure chamber. So you go from P1 all the way to P3. And so what happened when you flash like this, when you reduce the pressure on them, the water will separate into vapor and liquid, saturated vapor and saturated liquid, 3G and 3F. And how much of that m.1 become m.3G, how much will actually go to the turbine, it depends on the quality of 3. So if the quality of 3 is 0.2, that means that 20% of that m dot is now m dot vapor, right? So we need the quality of 3 to figure out how much m dot going to the turbine. How do you get the quality of 3? Well, if we know the entropy of 3 or the enthalpy of 3, we can compare it, you know, with those two guys, and we figure it out. So what is that process exactly from 1 to 3? From 1 to going through this chamber, this is throttling. It's constant H. So H1 is the same as H3. Okay, so how do you get H1? That's easy. That's HF at whatever temperature we are bringing the water from. And then you would say it's the same as H3. Now I have H3 and I can look at the table at H3F and H3G, and of course that difference over this difference is the quality. So I'm saying H3 minus H3F divided by HFG is the quality at 3. And again, that quality at 3, if it's 10%, 15%, 20, whatever number is, that's basically how much m dot 3G divided by m dot 1. Okay, and so that go into the turbine, and we have seen this before, right? So what do we do to figure out how much work going through the turbine? You need H3G minus H4. How are you gonna get this H4? First, let's try to get H4S. How are we gonna get H4S? If only I know the quality at 4S, I can get the H. How can I get the quality at 4S? Well, the entropy, same, because it's isentropic expansion. So whatever the entropy over here will be the entropy over there. Now you have the entropy over here. You go to the table, find what's H, what's the entropy SF, what's the entropy here, not here, it's SG, and then you tell yourself that delta S, S4S minus SF divided by the big difference, SFG, at that pressure is my quality. Now I have the quality I can use to calculate the H at 4S. How? H at 4S is HF plus the quality 4S multiplied by HFG, and you got yourself H4S. We did this before, right? Now we have H4S and we have H3G. You can get yourself the ideal work. The actual work will be a little bit smaller. By how much? By the isentropic efficiency of that turbine. So if you say it's an 82, 85 turbine, then you would say work actual is work ideal multiplied by the isentropic efficiency. If you got yourself another efficiency for the generator, then the output power would be even smaller by multiplying this efficiency times this work. Okay, so this is basically a flash liquid dominated geothermal system, right? So in one year I asked them in the exam I showed them the sketch, and I basically give them multiple choice, and I said, you know, is that flash liquid dominated or vapor dominated. And so how do you tell? You just look at a flash chamber and you can basically figure, it must be liquid dominated. That's why they need the flash separator. Also, a way to ask about those things is, I will give you this and ask for the TS diagram, or I give you the TS diagram and I ask for the schematic of the cycle. Alright, so I want you to be able to recognize either one of them. You look at this and you know it should be like this, or if you look at this guy, you should be able to plot the TS diagram. Alright, I remember fondly, when I was undergrad, plotting those TS diagram was one of my best experience as an undergraduate mechanical engineer. I loved, how we can convert this thing to those things. Right? So now let's look at what happened after we expand in the turbine. Again, we cannot just dump it in the ground. Why? Pressure here is very low. So whatever this condenser pressure is, it's probably gonna be way lower than the atmosphere, let alone that pressure. It's really it's gonna be high over here, that pressure. So we need to pump it, and we cannot pump it to that pressure when it's vapor. Why? It takes a lot of power to pump it if it's a vapor. But if you turn it into liquid by a condenser from 4 to 5, then it's super easy to pump the liquid. Pump work is very small. It's very small to the extent that, look at this. In the sketch, 5 and 6 are one state on the sketch. And that's what you do in the exam if you're running out of time. You would say pump at 6 is, or the pump work is neglected, therefore H6 equal H5. Okay? And now, unlike the previous sketch where he cooled the water and after cooling it he will dump it in the ground, now you can see he's a little bit smarter and he pumped it directly into the ground before cooling it. So he pumped it directly, and then the rest get cooled in the cooling tower. So 6 get cooled to 7, 6 get cooled to 7. This will probably be 0.7. How low 7 is? As low, ideally it will be as low as the air cooling that cooling tower, right? He cannot get lower than T ambient. And so what is H7? Well, it's gonna be HF at T ambient, right? So figure out what is the temperature of the air that he's using in the cooling tower. 25 degree. Then you get HF at 25 degree, and that would be the H that he sent into the condenser. This is direct contact condenser, meaning he's spraying the cooling water into the steam, which is 4, and both of them, 4 become 5, and 7 also become 5. So while the steam is condensed to liquid, the water is being heated to state 5, and both of them leave at 5. As we said earlier, because this huge delta H, it takes a lot of m.7 to cool the m.4. So to take m.4 from this H4 to H5, it will take huge m dot to go from H7 to H5. Okay, so first law of thermodynamics. The first law of thermodynamics. So you would say m.4 times H4 minus H5 is the same as m.7 times H5 minus H7. H5 minus H7. Okay? And so here is an example with numbers. Okay, and I will let you read it. And what he's asking for over here. Find the mass flow rate of the water from the well. He want m.1. He want to know this m dot. How we can get this? Well, how much does he need from here? How much is m dot turbine? Well, this is a 75 megawatt flash steam. So the work leaving this place, and he's saying that the combined efficiency of the turbine and the generator is 70%. So once you get yourself work ideal, hit it by 70%, that should be generating 75 kilowatt. 75 megawatt, not kilowatt. This is wrong. It's not kilowatt, it's megawatt. So to come up with that m dot turbine, you would say m dot turbine time h3g minus h4, h3g minus h4s, time the efficiency, the combined efficiency, 3g minus 4s, 3g minus 4s, times 70% will end up being the 75 megawatt. For that you get m dot turbine. So we are working the problem backward now. So we know how much is m dot going over here. Well, what is the relation between m dot 1 that he's asking for and m dot 3g? How they are related to each other? They are related by the quality at 3. Remember, x3 is m dot going to the turbine divided by m dot 1, right? So we need the quality at 3. How do I get the quality at 3? If only I know the entropy or the enthalpy. Any one of them will, we compare it to the difference, we'll be able to get the quality. We know the enthalpy. Why? Because H1 is the same as H3, because that throttling process keep the same enthalpy. So H3 minus H3F divided by HFG is the quality at 3. Right? And so that's what he's trying to do over here. See, he's trying to get the quality at 3 in this page, right? And then he's saying, well, then m dot turbine is m dot water time, that 0.161. So he will get the m dot turbine from the power, again power, the 75. This is, he's solving it for kilowatt now. I don't know. So I guess the solution is for 75 kilowatt rather than 75 megawatt. It doesn't matter, right? So then the answer would just be 1,000 times more. So he's solving it for 75 kilowatt. That's why 75 10 to power 3. Okay. So to come up with this 75 kilowatt m dot turbine, multiply by ideal work times the combined efficiency of the turbine and the generator. This equation will allow you to calculate m dot turbine. Take 158 kilogram per second to get this 75 kilowatt. If it was 75 megawatt, you multiply here by 10 to power 3. And finally, m dot water, how do you get it? Right? M dot turbine is m dot water times x3. That's what he's doing. And from that, he will get m dot water. Okay?